So when you look at mobile devices, they actually have a very similar structure to like normal computers, with the exception that you no longer have a hard disk. You instead have some card, some SD card, and you become much more concerned about energy and power because in mobile devices, the most important thing is that to keep the mobile running for as long as possible. Most people would appreciate having a weak uh, mobile device that can run for days over basically having a mobile device that can stream HD videos but can run for half an hour. So this is the most generic architecture for any computer system, where you basically have some disk, some peripherals like mouse, keyboard, printer, some graphic peripheral like a monitor, and then you have memory, you have CPU, and you have a network card. These peripherals are connected to the CPU, memory, and network. Sorry, using the system bus. The disks have a disk controller that controls their usage, and the monitor has a graphics card that actually renders and shows the video or the whatever you're displaying now. So, a modern OS will provide the following functionality. I know we keep coming back to this multiple times, but it's just like, yeah. So you'll have process and thread management. You will have concurrency support, and concurrency both for threads and also in terms of multiple things running at the same time. So you have I/O, which is basically storage. You're writing things to disk. You have processing. You have multiple programs running, and so on. You have the I/O devices, which is basically are basically things such as storage devices and different I/O peripherals like the keyboard and so on. You have memory management, you have file system management, and you have things for distributed systems like network and so on. Many of the architectural features in today's chips, in today's computers, are actually motivated by the operating system. So in this table, we look at how operating system concepts actually affected the way that hardware evolved. So operating systems, we have talked multiple times about the need for protection in operating systems. You do not want people to be able, do not want applications running on the same computer to be able to steal data from the other applications. If you're basically logging onto your bank account and at the same time basically browsing your Facebook, you do not want Facebook to read your banking account password. So you have protection, and hardware has evolved to support many of these protection needs by actually implementing the hardware with like kernel user mode, protected instruction, base limit registers, and we'll go through this. You have interrupts and the interrupt vector. So we talked about basically me not clicking or not typing anything for the past couple of minutes. Once I type or once I click, I cause an interrupt, and then there is an interrupt vector implemented in hardware. We'll look at it more closely during the course that actually handles whatever I do. So if I click the mouse, this should mean something. If I type on the letter P, this should mean something. If I type on the function key, this should mean something. You have the system calls, and these are basically the interface between your you as a user or your user programs and the operating system. And hardware support has evolved to have like trap instructions and trap vectors, which we're going also to discuss a bit in the course. You have input output support, basically what happens when you type, or when you plug in your USB device, or when you plug in some device in general, something happens basically, and there are interrupts and memory mapping to actually help you manage these input output services in the operating system. And for example, when you plug a USB stick or an external hard disk, you need to map it somehow to your system. You have scheduling, you need error recovery, you need accounting in your operating system. We'll talk about these also. And hardware support has evolved to have a timer, basically, that enables you to, for example, run this program for X milliseconds and run the next program for Y milliseconds. You need synchronization. You basically want to make sure that there's synchronization between different parts of the system, and you have atomic instructions in hardware support. We'll talk about some of this. You have virtual memory, and which is how you actually handle memory in the operating system. Talk about this, more details. And in hardware support, you have the TLB, the translation look aside buffer. So let's look at the first challenge, protection. How do we execute code with restricted privileges? You do not want my code to interfere with your code both running on the same machine. Either because code is buggy, well, I am not a so good programmer, or it might be malicious. I might actually want to steal your password. So there are many reasons you want protection. Some examples, you have a script running in a web server, in a web browser, sorry. So there are many of these client-side scripts that run on your browser using, for example, Flash Player and these things. And you want to make sure that this doesn't actually hijack your whole computer. You download a program from the internet, you're not really sure what will happen with it, and you write a program, and that program might be very buggy, so you might cause a memory leak on your computer. You might have you might go into an infinite loop. You do not want your computer to completely stop functioning because you wrote a wrong program. Of course, this is the theory. Of course, practice is different because, well, all of these things happen. But an operating system, to design an operating system, we actually wanted to have protection. So one form of protection that hardware actually provides also support for is the concept of privileged instructions. And these are instructions available only in kernel mode. A computer, in general, runs two kinds of programs at the same time. You'll always have the kernel running, you'll always have the operating system running, and you'll have the applications running on top of them. So hardware architects, along with operating systems people, came up with the idea that maybe we can have some instructions that are only available for the kernel to run. So as an application, you cannot run these instructions. You can ask the kernel to run these instructions for you, and the kernel can decide yes or no. Many of these instructions will be hardware related. For example, memory accesses. If I'm trying to access different parts of the memory in my computer, the kernel handles that. It's not me as a user who actually handles that. Changing processor flags, because there are many flags in the processor that we'll talk a bit about them, and you do not want the user to be able to change the way that your processor functions. If an application tries to use a privileged instruction, a processor exception occurs, and this is an instruction, of course. When a processor exception occurs, the exception is handled by the operating system. And one way to actually handle it would be to halt the process. So basically stop the process because it has been trying to access an area in the memory that has not been allocated to it. CPU supports a set of assembly instructions. These are mostly assembly instructions. For example, all of these: move, add, move control register, which is basically you're moving things that are related to how you control your system. Input string, hold, load task, register, software interrupt. All of these, or many of these, are actually sensitive or privileged. So things that you can only run in kernel mode. So your computer run actually in a dual mode. You have the operating system, which have full access to the hardware because it controls the hardware, and you have the application that should not be able to access the hardware without explicitly being allowed to do it. So you have a dual nature for every computer that is running today. It runs either, I'm currently running in both as both user and as a kernel. You go to the kernel mode space to execute complete privileges. So privileged instructions, you need to be in the kernel mode to basically manage the whole operating system. And you have the user mode, which is basically you execute with lower authority, with lower privileges, and you have basically more safe mechanisms for people to write their software. And you need a safe way to jump between these two modes. And how do you switch from one mode to the other? So if we look back at our processor, that basically flow that we were discussing, you have a program running, you have basically select the program counter, you basically select what line in memory you're going to read. You basically go and fetch that line in memory, you execute it on the CPU, and you either go and fetch the next line in memory, the next command, the next instruction, okay, by adding an offset to go to the next memory location. Or if it's an if then else statement, for example, you might need to branch and then you change the whole program counter that you're going to use. You basically jump in memory and go fetch a completely different block in memory. This was the simple way that your processor operates. Now with the privileged mode, you actually even have to have a bit here that basically tells the processor if what mode you're running in. So if you're in privileged mode or kernel mode, you have no checks performed on the instructions. So you basically, anything can be done if you're in kernel mode. And this is basically done by setting a register saying, this is a register. Yeah, you basically set this register to either kernel mode or user mode. So if you're in kernel mode, everything here is vanilla. Everything here can happen, okay? If you're set to user mode, then, well, you cannot do everything. You need to do some safety checks. And the processor does that. It basically checks, for example, if you have a branch address that you're going to jump to, for example. So if you basically use a jump statement, some programming languages provide jump statements. So if you're trying to access some memory, then the processor basically checks if this is allowed or not, and you check all the bounds for your application. So this is how processors operate in dual mode. So if you look at basically the way that protection is done, you have ring 0, which is the kernel. It can do everything and anything. You have the most privileges. You can touch anything. You can do anything. And this is why messing up with the kernel is very dangerous, because if you write the wrong kernel, if your kernel is not secure, your whole system is basically not secure, because it can do anything. Anything that runs in kernel mode can do anything. Then you have the device drivers, because some devices, for example, if you have a hard disk, the hard disk should be able to do some operations that are related to the kernel, but they are not really related to, for example, the CPU, right? So in many of these device drivers run in a state that is between applications and the kernel. Device drivers are basically control softwares to your different to your different devices. So some of these devices require some privileges, but you do not give them all the privileges that you give to the kernel. So device drivers, as we will see when we talk about the Linux kernel, are actually implemented as separately from the inner core of the kernel. And then you have a second set of device drivers. For example, you connect a printer to your computer. Okay, you need a device driver for this printer because you need to print and you need to access some of the hardware mechanisms. But that does not mean that just plugging in plugging in a device enables it to be in kernel mode, because that would be very dangerous. You can just plug in anything that is malicious, like you can plug in a printer that overtakes your computer. That would be funny, actually. So this is why you have these different rings of operation for the actual code that runs on your computer. So you have the kernel code, touches everything, changes anything, can basically burn your computer. Okay, can literally burn your computer. You have the device drivers, which can access some things. I mean, for first set of devices like your hard disks and like your keyboard, they can access some things, but they cannot access the internals of the kernel. They cannot change the scheduling, for example. You do not want basically some vendor to build his device driver. So because if you buy, for example, a network card, mostly the vendor comes up with a device driver for this network card. You do not want that vendor to basically control your whole computer and make his device the fastest thing on earth while everything else is slowed. So this is your second ring. Then the third ring, less involved devices. Okay, and then your applications. And you use basically this mode to actually control what happens in the system.